So the topic again is reliable uses of two-dimensional hydrodynamic flood models in stream restoration design. And I'd like to thank our presenters for joining us today and sharing the important work that they're doing. So just to let you know a little bit about our presenters, Jesse Robinson is a senior water resource and environmental engineer with Wetland Studies and Solutions. He specializes in the design of high-functioning stream and wetland restoration solutions in the eastern United States. His design experience ranges from highly concentrated urban environments to large rural headwater basins with miles of connected stream and wetland restoration. He has extensive experience in natural resource assessment, terrain development, design, and optimization of restoration strategies from concept to implementation, and hydraulics analysis, primarily through two-dimensional hydrodynamic modeling. Thank you, Jesse, for being here. We also have Dr. Art Parola with us as well. Art is a principal engineer with Wetland Studies and Solutions. Art specializes in designing stream and wetland systems, riverine mechanics, and sediment transport. He's an expert in two-dimensional hydrodynamic modeling for stream and floodplain restoration and vulnerability assessment for infrastructure design. He has directed the design for more than 275,000 feet of stream channel and hundreds of acres of riparian habitat restoration, including floodplain wetlands. He has partnered with state and federal agencies on projects that require complex riverine modeling, including 2D hydrodynamic modeling and sediment transport analysis. Art has extensive experience with urban restoration and has designed best management practice approaches for urban outfalls, bridges and culverts, and other infrastructure. So again, I want to thank our speakers for being here and sharing their important work. With that, I'm going to stop sharing my screen and I am going to turn it over to our speakers.
Okay, well, thank you, Missy, and thank you, Michelle. I'm going to begin sharing my screen here. Is everybody able to see that, Missy? We're good. Okay, great. So that was a great introduction. So I'll just jump right in. The structure of the presentation today, I'm going to give an overview of how we apply two-dimensional models in stream restoration design, really beginning with the site assessment phase through the refinement of design. The reliable component of this presentation, that's the start of our title there, comes from the fact that these models, the sites we're using in this presentation, I should say, in some way we've evaluated the reliability. That's either through our Chesapeake Bay Trust funded study, which recently concluded. We have several examples from there, or the case studies that Art's going to present at the end. We have some evidence of the effectiveness of the model and showing us how the project is working as designed. Or in many cases, a few of the examples I'm going to provide, we've worked in analogous environments for a decade or more, seeing how these models allow us to create designs that are functioning as planned. Stream and wetland restoration covers a really wide array of techniques and areas, from the images I'm showing here, which are in the headwaters of the Daniel Boone National Forest in Kentucky, to some of the work we've done in the Chesapeake Bay. So I just wanted to present a few examples here just to expand our understanding of what stream restoration might be. These first two images here on the left, you've got a photo taken in a site here in the Daniel Boone of a reach before restoration. So you can see the channel bed is consisting of bedrock. There are steep channel banks on both sides. It's been straightened, which we know from site investigation and historical evidence. So our objective in this project was to reconnect the channel to its floodplain while maintaining a connection to the groundwater. And so to achieve that, here on the right, we're showing an aerial image now of the completed restoration several years in. To achieve that, we constructed a new floodplain with a small base flow channel moving through it. We were able to preserve this remnant forest stand in between here. And then the old channel was converted into a series of open water wetlands and ponds. So now we're in the lowlands of the Chesapeake Bay, and instead of developing a floodplain restoration or stream wetland complex, the designers here were using a series of structures called beaver dam analogs, so wood structures consisting of posts, logs, root wads that raise the bed of the channel up to reestablish a floodplain connection and reverse a lot of this severe erosion that was occurring in the channel bed. Both of these, the first example here I discussed and the second, are forms of stream restoration. They look very different in terms of the techniques that are used and the location. The important thing here when we consider how we might use 2D modeling is each of these approaches and many others that we're not gonna spend a lot of time discussing have in common some things that allow us to use 2D models, like alteration of the geometry of the proposed channel and floodplain. So almost every restoration site is going to have some degree of alteration to the existing geometry. The use of grade control structures, those may be woody in nature, like the beaver dam analog I just showed, or rock in nature, as we have with natural channel design or riffle construction. So those may be input into the model as part of the terrain or separately. And then we have choices about the material characteristics. So the wood, the rock we're placing, how the floodplain and channel banks are going to be vegetated. All of these form inputs to the 2D model. So we can combine those inputs with a few other things, including our model boundary conditions and settings, to develop a 2D model. Point being that we have a lot of the data as part of the restoration design process to facilitate the use of 2D modeling. So in site assessment, 2D models have this really interesting role to play in effective planning. Early on, you can get a good sense for the existing vulnerabilities and how we might address them through a combination of observations on the ground and the use of 2D models. There's also a role for 2D models to play in the beginning to consider what the possible design methods should be. Often the case is, especially on larger sites, that there's a role for multiple design techniques. And it could be that running an initial 2D model at this stage will help you generate questions about what methods are most appropriate for different areas. It will also help facilitate conversations between you as a designer and the regulatory community, your project sponsors, whoever else is involved in the project. And finally, it helps us envision, even at the early phase of the project, what we might create and how it might function. So what kind of habitat and function we would get out of the project. Here I'm showing the pre-restoration condition of a region in Kentucky called Staggs Branch. We're going to show a variety of 2D model output in the presentation, so I'll just take a moment to point out in general what we're looking at here. These cooler colors, the blues and greens, represent a lower velocity condition. These hotter colors, reds, purples, pinks, and whites, represent a higher velocity condition. So in this case, what we can see is the 100-year flow is entirely contained in the existing channel, and we have evidence of very high velocities over 6 feet per second virtually everywhere in the channel. Right away, that's going to tell us that there's a strong likelihood of erosion of the bed and bank materials. And if there is sediment moving through the network, we're likely to see deposition and erosion of that material based on the flood velocity simulation we have here. So it starts to orient you as a designer and anyone else involved in the project to the nature of the vulnerabilities on site. 2D models are not used in isolation though, right? So getting out on site, walking around, really understanding the characteristics of the site, that's still very important. And what happens when you pair these two things together is you'll develop an understanding of the site. Maybe you've walked it first, or maybe you've looked at the model first, and they'll tend to help you consider all the possibilities. So here we are walking in a site on the eastern shore of Maryland, and you can see this extensive erosion along the banks on both sides. The network is incised dramatically. As we walked around, we thought that there was the likelihood that most of this was due to weathering and not as much due to scouring due to flood forces. So we had that initial idea, and then as we ran some of these 2D models on the existing condition, we realized that the flood velocities were quite low. Now we have an understanding that we can feed into the design. So what we were able to do was focus on addressing the issue while preserving as much of these existing resources as possible, these really large mature trees. There's also this role now, as we understand the output of 2D models and as this technique has become more mature, to consider what this is going to look like even at the earliest conceptual design stage. So this is a creek in Anne Arundel County, Maryland, Furnace Creek, that we used as part of our Chesapeake Bay Trust funded research. It was a concrete lined concrete lined ditch before restoration, and now is a floodplain restoration project or stream wetland complex. So our question using this site was, can we understand, based on the output of the 2D model, what different areas on the ground would look like? So the evidence left by flood disturbance in terms of manipulation of vegetation, patterns of erosion and deposition, could we get a better sense, a more refined sense of what the 2D model output is telling us about how this will look post-restoration? As part of that work, we defined these 4 different categories of stability and how they retain organic matter and sediment. We don't have to get into all the details here, but what I will say is these are basically a range of behaviors that every one of us can observe if we walk sites over time. You'll see in certain sites there's very little evidence of flood damage. So the vegetation is undisturbed by flooding. There may be water around the vegetation, but it's a very low velocity, so it's not knocked over. It's not streamlined in any way. Also, you'll see that the ground, there's almost no disturbance to sediments or organic matter. It's all kind of sitting there because the velocities are too low to move that material through. On the other end of the categorization here, this 4th category, that's where we have widespread erosion and instability on the ground. In between, we see these 2 sort of transitional categories where category 2 is, you can see evidence of flood disturbance, but it's non-destructive. So the vegetation's laid down, maybe there's some local sorting of material or organic matter, but generally the site is intact without evidence of damage. The 3rd category is closer to threshold conditions. So you'll see locally some erosion around the base vegetation or movement of sediment or organic matter. So we develop these categories, and then we characterize different areas within the site. What we found was this distribution of velocities within each category that describe these semi-distinct ranges of velocity that are associated with certain behavior, meaning certain kinds of flood disturbance. So the 2D model is telling you really useful and interesting things about what this site is going to look like. This site, like many others, is constructed for TMDL purposes. So if we're after, sediment retention and nutrient reduction, it's really helpful to understand what kind of velocity conditions are going to prevail on your site before you invest significant resources into designing it, because that might tell you how it's going to function later and how you might achieve those objectives or not. Another really useful thing we can consider even in the site assessment phase is the role of infrastructure. Art's going to have some detailed examples to show about how we consider infrastructure in design, but from a broader perspective, how might we think about this early on in the project? This is a site, Bear Branch and Prince George's County, excuse me, in Maryland. And there are 2 roadway crossings at the downstream end of the project. So during the 100-year flow event, which is what I'm showing here, those 2 crossings, because of the size of the openings, are backwatering the entire area of the restoration. So what that means is the flood velocities, the flood forces on the restoration are really low during that event because of the backwater. If we remove the influence of those roadway crossings, you can see that suddenly we've gone from a really low velocity condition to a really high velocity condition. Now this is artificial. This is an example. Those roadway crossings are there. The highway is there, and there's an embankment there. But it shows you, okay, the influence of these structures is so great that I probably need to understand, at least at a gross level, what they might do to my prospective design as I'm considering it early on. So to move now from site assessment into the design process, there are specific things that 2D models are really helpful with. One is to identify areas and components that are most vulnerable to flood damage. And we'll talk about some specifics there. The other is to facilitate what we call iterative design. And I think a lot of engineers use iteration in different ways in their design process. 2D models have a really specific way of aiding that iterative design. And then ultimately, designing for resilience and function while minimizing our disturbance to existing resources and the cost of our work. I showed earlier that the analysis from Furnace Creek, where we were looking at the distribution of model velocities and the observed behavior on the ground. So that's one component of the model output. That's the velocity magnitude. So how fast or slow is the water moving? Another thing to consider is the direction of water, or the pattern of the flow. We're now back at this Bacon Ridge site that I referred to in the beginning of the presentation, the one using Beaver Dam analogs. What we found when we investigated the flow pattern around those structures was a close correspondence between the predicted velocity direction and the observed velocity direction. That's a really interesting finding because these structures are very irregular and each one is unique. So if you look at the geometry of the posts, you can see it in this picture, there's a network of posts across the channel, there are root wads sticking up, there are logs. It's highly irregular. You have to have the terrain to represent that irregularity. But if you do, the 2D model is very effective at taking the obstruction or lack of obstruction due to those woody elements and determining where the flow is going to route depending on the opening sizes. So from a design standpoint, we can consider where the flow is going and what the intensity is, the velocity magnitude. Now we're at Furnace Creek again in Maryland. This is showing an area where, this is related to our ability to identify vulnerabilities and correct them. This is an area where you can see the channel embedded in the 2D model output here. There's a little local hotspot in the model. What's interesting about this hotspot is that it shows up on the proposed design. It shows up on the as-built, meaning we've gone and surveyed the site and rerun a model on that. And in that location, there is some local erosion. The designers were aware of this, I will say that. So they knew to place rock under the area. So they had run a 2D model and determined there was a local vulnerability and corrected for it. But just as due to the nature of the site, which is, there are houses on both sides, the reach narrowed here and steepened, and there's just this little bit of bypass that's occurring with the flow on the right side, creating a local vulnerability. So 2D models are really good at helping us as engineers see those local vulnerabilities and address them. Could be that we can't do anything in terms of the geometry because of how we're constrained or because of the potential to flood neighbors. But at minimum, we'll know that we need to protect the area so that we don't initiate head cutting or downstream transport of sediment. Back to that very first slide I showed of 2D model outputs. This is Staggs Branch in Kentucky. This, again, is the existing condition for the 100-year flow. So you can see all of these really high velocities throughout the channel. We have now done enough design in this area to have a sense for how we might address this high velocity condition. So this is our draft design. This is about a 70% design. So if you're looking around, you'll notice some defects in the surface. This is still draft work. But what we have done here is go from flow, which is entirely confined in this very deep existing channel, to a small base flow channel moving through an active floodplain. We have sized the geometry and the planform curvature of the channel and the geometry of the floodplain using 2D models throughout. So it's helped us first consider, okay, what should the geometry of these be? What existing resources are in the area that we want to avoid? There could be some larger trees or some culturally sensitive site. And then we bring all those constraints into our project and iterate through the design with the goal of creating a solution that we know will provide, high value aquatic habitat while also being resilient to flood damage. Resilient in this case means that we have low velocities during the higher flood events, or we have provided some sort of countermeasure, some rock or other, maybe erosion control blanket to protect against erosion. So I'm gonna turn it over to Art here. I just wanted to leave everyone with this this thought that comes just from how I use these models in my everyday work as a design engineer. They're a really effective companion to the design process. This is a site in Kentucky called the Boston Restoration, and it's a really flat area where our initial analysis showed us that the flood forces were really low. So we could do creative things with that, knowing that we weren't likely to see erosion due to flooding throughout the site. We really pushed the planform curvature of the channel, included a lot of pools. We included a lot of floodplain pools, so that if you look at this constructed floodplain down low here, most of the area is wetted habitat of one form or another. Because there were few trees of any value here, it was mostly just small 1 to 2 inch cottonwood or green ash. We were also able to sidecast the material as we were building the site. So that saved us a lot of money in the construction process, which then allowed us to do things like create additional wetlands off to the side here. We also used the 2D model to consider how the river backwater, there's a river downstream that's backwatering the site frequently, how we might use that to create additional wetland areas. And this is at a point in the project where we still have a bypass channel in place. But later in the project, we essentially took this bypass channel out and created additional wetlands over here and sized those openings, the openings to the wetland, using 2D models to consider how much water we could store. So they're a really effective way to get a sense for the overall vulnerability of the environment and then start the creative process of design, because you know where your constraints are, you know what the vulnerability that you must address is. And so it puts these kind of guardrails up to think about effective design. And with that, I we'll transfer it over to Art.
Well, I think Jesse started out to talk about the creativity in design and the use of 2D models. And I think to this point, a lot of what we've done is use the 2D models to identify vulnerabilities. I think people have doing that for quite a while now. So the two parts that I think were the models are starting to, if you really understand the models and you understand sites and you understand design, it's going to lead to maybe some more creative solutions to a lot of the problems we have because of our ability to see flow pattern. Jesse mentioned flow pattern. I'm going to talk a lot about that as opposed to just talking about stress and a little bit about the direction of flow, but the overall flow pattern that we see and then how we can use that to improve designs and really understand problems better at sites. A lot of times I find that a lot of time it's not the stress necessarily in the channel, but it's the transfer of water from the main channel to the floodplain, or there's a bridge or some other transition where there's some strange kind of, say, flow pattern going on that you might be able to alter to a different flow pattern. And so that's kind of going to be my theme here going out at the end of this is to think about the flow patterns along with the stress and how we can creatively either understand what's going on as problem at a higher level for solving stream problems or restorations or designing restorations. So with that, I'm going to go with two different examples, and one of them's a transition design. It's from a culvert to a stream restoration. It's going to involve something I call rock diffuser, where the flow is coming out of the culvert and then transitioning into a restoration. But this could be kind of thought of as almost any outlet design. And I'm going to show an alternative way of doing things that involves the model. And the second thing I'm going to do is talk about a constructed riffle design project that we had. We're removing, in fact, it was a redesign of a project that didn't meet mitigation objectives. But basically, they were removing two water crossings that were acting as dams, like 6 to 8 feet of elevation change. And we had to go back in and put a couple of constructed rock riffles that were very expensive, on the order of $250,000. So we were trying to figure out how to place them. And I want to show some alternatives and how the looking at the flow pattern was instrumental in those two things. So the first one here is at Furnace Creek. And there's a culvert in the upstream end here. The water's coming out of the culvert into this pool, and that's a very common thing. People call it energy dissipation pool. And if you look at the rock here at the downstream end, the field evidence, you'll see that this rock is exposed right here. And on this side, the rock is not exposed. I think probably when it was placed, it probably was all exposed, but there's been some deposition here. And obviously you can see the higher velocity water coming off to the side here. So we have flow coming out, and we expect that the flow is going to go out of this culvert and just sort of diffuse and widen out. And we were doing a lot of one-dimensional analysis. We would say that the water would basically expand at a rate of about 4 to 1. So every foot downstream, it will go down a foot and then widen a foot. So we're counting on this pool to do some kind of energy dissipation. But we can see clearly here that there's something going on, because these rocks are clean, this the sediment's being scoured, and this material isn't. When we run the 2D model, what we see is something like this, where flow's coming out of the culvert, not really expanding a whole lot. And then there's this large pattern, this large secondary pattern of flow recirculating here. And you could see how that would cause sediment coming along this way might be dumped in here. In fact, you can actually look carefully at it. You could see the flow pattern coming back this way and then coming back up to here. There's actually debris up in here that's stored. So you think that this thing is widening, but what's happening is the water's kind of blowing through and doesn't really start to expand till you get to the downstream end of this. So the question is, this is like, it was probably 60 or 80 feet long. The question is, do we really need it to be that long? Is this really dissipating energy the way we think it should dissipate the energy? So, I wouldn't have known this. Like, it would be really hard to go out during the flood. I guess if you paid close attention to the pattern, you might be able to see this during a flood. But what the model does is give us a pretty clear understanding that this is really not dissipating a whole lot of energy, and it's really just kind of blowing through the pool here. We noticed it at other sites a while back, and we tried to make something that would transition flow from a pipe to the rest of the channel in a very short distance, like the shortest distance possible. And this is a site in Lexington, Kentucky. It's like a half square mile watershed, very urban. I think it's like probably 80% impervious area. Basically just a bunch of parking lots and streets and rooftops upstream. And it comes out of those two pipes. And then it comes into an area that we were restoring. So we thought that if we put some kind of obstruction in the way here, like many other energy dissipators are that through the Corps of Engineers, there's something very similar to this, but we want it to be a bit more natural. We thought if we put some obstruction here, how big does that obstruction need to be so that we could transfer the water from these pipes during flood so that we could, as quickly as possible, spread the water, diffuse the water across the floodplain. And so here's our model over here. This, again, we had a bunch of simplifications. We modeled these rocks as just a plate. We modeled not two pipes, but just one area here with the total flow, the total momentum of the flow coming out of the pipe hits this obstruction. And what we're trying to do is get the water to the momentum of the flow to be dissipated or diffused, so that by the time the water got over here, it was going pretty slow. And these are shear stress contours, but the overall pattern is pretty clear here. Really high velocity, high momentum, and by the time it gets out here, the stresses and the velocities are pretty low. So fortunately, we had a flood event during construction. I guess fortunate for me because we could take pictures, maybe not for the construction crew. But I wanted to show you some of the images here so that you could see what happened, and some kind of verification that the 2D model, there's a lot of 3D things going on here, but the 2D model still conserves momentum in 2 dimensions. So it is an effective, if it can be an effective tool. So here's water coming out of the pipe. You can see it's going pretty fast, hits the rock, and basically explodes into the air. So it goes vertical. And then as it goes vertical, it creates the turbulence. It changed all the momentum of the flow coming out of the pipe into turbulence that then has to flow away sideways here and out. And you can see by here, like in the model, you see a couple of veins of high water or velocity, relatively high velocity compared to what's downstream, but much, much lower than the velocity coming in. Just to kind of give you can see even that log, you still have some recirculation going on up here, which we also saw in the model on each side. But for the most part, we've dissipated the energy by maybe absorbing all of the momentum of the flow of that water coming out and forcing it to flow away. And just to give you another perspective there, I'll go right to now we're looking on the road, looking downstream here. So you can see the water kind of, whoops. The water coming out of the culvert this way, hitting the obstruction and go out. And the idea is, how big does those rocks need to be? How wide do they need to be? How far downstream from the entrance? You can go to a standard Army Corps of Engineers engineering manual to look at energy dissipators, but this is a specific site, has specific constraints. So the idea that you could use the model to understand the process and then properly size the rock for this specific amount of momentum coming out of those pipes and the specific constraints of the valley bottom to get the flow to go away down here at a relatively low velocity and fairly uniformly out onto that floodplain was a key to this project, or the key to our understanding. Now, every time we go to one of these pool transitions, we're thinking about these kind of problems and the solutions to those problems. So this is there's the pipes up at this end. Here's the restoration going through. Here's the, again, an aerial view. Water's coming out of a long pipe here. There's the diffuser and into this tiny little stream. It's an urban stream, half square mile, very tiny little stream. I think we didn't even build it. We just let it kind of form. And then here's the project, probably a year or so ago, with all the trees growing in the valley bottom and a stream wetland complex below, and the diffuser at the upstream end. So that's one kind of demonstration of how we can get creative with these models. The second one here is just an alternatives analysis. We have a constructed riffle and with a redesign of a mitigation project. And again, we're moving to two small dams. So we're having to drop 13 feet, approximately 12 to 13 feet over a relatively short distance. And how do we make these constructed riffles? Are going to be expensive. So to give you an idea, this is a kind of right from the design. It's actually the thing. These are the displays that we used with our client. Which was Kentucky Fish and Wildlife. And on this, there already was a parking lot over here, so it was a high spot. And on the other side, there was a fill that contained the concrete from the removal of the crossings. And what they didn't want us to do was to cut. This is our first draft. We're actually cutting into a fill that they had here. They really didn't want us to do that if we didn't have to, because we would expose the concrete. It's in the Daniel Boone National Forest. They didn't want us to. They want us to minimize the cut there. So there's also a road that goes to access an absentee landowner that's on the other side that had to be maintained. And we had to drop about 5 or 6 feet right here. It's a 10 square mile watershed, so it's a pretty decent flood. So this is one view of this, and you can see there's a little bit of recirculation going on down here. Might want to pay attention to that. And so here's another alternative. And immediately you could see, right, we're going from the original to the new one, and you could see that the pattern has changed dramatically. By us putting in not cutting as much and then placing some fill here, we've changed the pattern quite a bit. And we get this big recirculation zone, and we push the flow over to the side here. End of the project's just down here a little bit. So we started to create some other problems. And then so why don't you realign this a little better? And we tried that. And so we moved the berm over here. Now we have to relocate the road, and there was a tributary coming down the side here. We have to relocate those now, and we still have this large recirculation zone. We really couldn't move it much further. So I guess my point here is you can look at the flow pattern, and you can come to some big picture ideas here about what your next step or your next alternative might be. And the other thing you do is communicate this very well to the client. When we talk to Kentucky Fish and Wildlife, we say, well, we tried this, and here's the reason why these won't work. Or we need more money because we need to extend the riffle, or we need to change, we need to make more fill or more cut, whatever it is. It's a great tool to explain these things and to understand them. So in conclusion then of, the models are really good at identifying vulnerabilities. I think many people understand it already. And whenever I go to a site, even if it's the first time I go there now, because LiDAR is so prevalent, I will try to sneak and run a model so that when I go there, I kind of have some understanding of the flow patterns of the site and some understanding. It's a lot of exchange with the main channel. It's everything in the main channel, what's going on. I can probably run these now much faster than a 1D model because the way that the new models are constructed. Especially we still use 2Flow because we think it's the simplest one to iterate fast, but other ones are coming along, and it's soon maybe is useful. Facilitating communication. If you've understood this and you're not and you don't really do this kind of design, you're not really used to looking at models. I think we were able to communicate at least some of the issues that are pretty complicated in a relatively quick way, and we really feel strongly that it's a good way to communicate with both agencies and other stakeholders. And finally, I think as we understand more about how these models and they get faster to use and easier to use, and the data is more available, I think it's going to put more creativity into the things that we can do, solving stream problems. but also to provide some really more interesting design in restorations and in transitions in urban areas. All of these things can come from our better understanding of the flow patterns. I'll stop there, and we'll open it up to questions.
Excellent. Thank you guys so much. That was wonderful. We do have a few questions. So let's go ahead and start right up here. I think you might have answered one of these. Which 2D model are you using for computational? Did you answer that one or no?
I think so, but we use, I mean, the company, Wetland Studies and Solutions and Davy Resource Group, we have people who run all the different kinds of models. People run HEC-RAS all the time. We have people who run SRH2D, which is a lot of times used by the highway departments. And we also run 2Flow. When we currently like 2Flow because it is the grid development is almost instantaneous. It's extremely fast. If you ask people what do they spend most of their time on, you'll see they'll spend a good chunk of their time developing grids, and that's improving all the time. But with 2Flow, it's extremely fast. It's really easy to drop in a new plan right over top of an existing condition, and it's extremely efficient. So our workflow works very well with 2Flow currently. But where, HEC-RAS is doing some things to catch up, and in terms of the speed of the model and some other things that make it more efficient for iterating. And really, iteration is the key here. How fast can you iterate and develop new alternatives and solutions?
Excellent. We have a couple more of sort of modeling questions, so I'm going to give you a couple of them so you can answer. Are there any situations where 1D models are more appropriate? And another one on the same is how are 2D modeling more effective in divided flow conditions?
Jesse, you want me, or you want to do that?
Well, I just in terms of where might 1D be more appropriate, even though the cost of running 2D analysis is small compared to the other aspects of restoration, there is still a cost. And especially if you're working on larger projects where maybe we're restoring an entire basin, as you move farther up the network, we find that there can be that the advantages of 2D analysis will diminish. If you're up and you're at like 2 acres of drainage area and the 2D model will predict you have flow 2 tenths deep, at that point we might simplify it to some 1D analysis, maybe just Manning's N calculations and those kinds of areas. There are others, but that immediately came to mind. Art, I don't know if you want to answer the divided flow question.
Yeah, I think anytime I just talked about flow pattern. With a 1D model, an engineer has to kind of envision what the flow pattern might be, right? They don't know, like when flow is coming out of that culvert, they would probably envision that it's going to expand at 4:1. Well, that's a bad assumption there. So whenever you're doing 1D analysis, you're assuming a lot about how flow is the overall pattern is occurring. And that assumption you use to develop your model, put cross sections, locate cross sections, things like that. Well, with a 2D model, you don't. So whenever pattern is important, so you have divided flow, the flow pattern becomes important. Or going around curves or bends or transfer water from then 2D makes way more sense. The other place that 1D is probably still the preferred model is when you're doing a flood model when you're doing a floodway model. All the procedures and processes are in place. So from a 1D standpoint, regulatory is relatively straightforward with getting FEMA floodplains, that kind of thing. Although they're starting to push more toward 2D, but the regulatory community knows what to do with a 1D model, whereas with the 2D models, it gets to be a little bit more complicated.
Excellent. Thank you for that. We have another one. Can you speak to the uncertainty associated with modeling 3D processes with 2D models, like accuracy of velocity estimates, and whether you've observed issues in the field where this was brought to your attention?
Go ahead, Jesse.
It's a great question. I think just as Art said, when you're using a 1D model to evaluate pattern, you as the engineer have to decide what the expected pattern is. There's something similar that can happen with the 3D aspect of the unrepresented aspect of these models. You have to know enough about the model to know when the local estimate will be less reliable, not completely unreliable, but less. And so this is a constant topic of conversation in sites that are more confined, where, for instance, the flow depth is much greater than it is wide. So we're trying to think carefully when we're using models in these environments about where might it underrepresent high velocity regions, and how can we look to the model data in perhaps more reliable locations in the vicinity. And we may even do something like an amplification factor to consider what the unrepresented component of that would be.
Excellent, thank you. We have another one in here. Do you typically model rock riffles or other grade controls as structures within the model as you would with a culvert, or do you simply have it baked into the terrain and Manning's layers?
Go ahead, Jesse.
Yeah, another great one. It depends, I think, is the answer. So let's say it's a site where we have thousands of individual grade control structures, and the amount of drop over each structure is minimal. In that instance, it may be that we bake it into the terrain. But if there are large structures that are, at minimum, you want to make sure your terrain is hitting the crest of those structures, so the controlling elevations on the structure. It could be that we input those as break lines so that the conveyance is calculated exactly where we want it to be. Very situational. So I think, again, it just comes down to, you want these models to be run by someone with enough expertise that they understand the relationship between output and input.
Jesse, I think what you said there, though, was that the terrain just gets more well-defined, right?
Yes, right.
Yeah,
And
you're
some
still
models,
modeling it as terrain. We're not like changing it to a culvert structure or something that's 1D or something like that. The bridges, the culverts, we're trying to, well, sorry, go ahead. It's still
no,
terrain.
that's a good point. That's a good point. I was thinking about how you would update the terrain, using that specific structure location. But you're right. We are not typically doing a 1D link where we
And
have a
maybe if
structure.
we're looking closely, we're also going to reduce the grid resolution, or usually we're pretty small anyway, but you might want to reduce the grid resolution to refine it to reflect the situation right at those obstacles, if that's your goal.
Excellent, thank you very much. So there is a question in here that is, I think it's, what are the points represented on predicted versus observed velocity angle? I believe that one came in right around the time you started talking about the Beaver Dam analogs.
Yes, thank you for the question. So, Art, yeah, if you're able to get back to that.
Did I go past it?
I think so. Oh, there it is. Great. So, so these colors represent whether, in the case of the gray colors, that's flow exiting from the channel. Orange is flow returning to the channel, and green is where there was a misclassification. The observed flow direction is different from the predicted flow direction. We were, trying to consider whether there's some differences in the effectiveness of the model in the outgoing versus the incoming flow. And generally, it's pretty close. But there was a little bit, a little more clustering, as you can see there in the plot, with the flow that is returning to the channel.
Great, excellent, thank you. And we have one more, which I think we still have 2 minutes time. So it says, great presentation. Recent studies suggest that Manning's N values used in 2D hydraulic modeling are often lower than those used in 1D models, depending on mesh resolution and detail. However, the findings are not yet definitive. In your experience, have you found that using lower N values in 2D simulations yields more appropriate results compared to 1D simulations with traditional N values?
I mean, to do this one, Jesse?
Yeah, that'd be great.
So probably you're going from something that was derived under the Manning's value that was derived under one-dimensional conditions. And there's a lot of thinking out there within 2D because you're representing some of the bend conditions and the increase in length of the flow and some other things that the N values are probably, the ones you would use in one dimension are probably too high and should be a little bit less for 2D. However, I guess there are so many other issues going on with knowing the flow and knowing other things that I think it's probably something not to worry about too much unless you have to match for flood flows of some kind. And if you're matching for flood conditions for a FEMA thing, um, then I guess you need to match them in some way, perhaps. I don't do a lot of the FEMA work, but we have others in our company who do that, so I'm not really sure what people are doing there. But as far as looking at flow patterns, stress conditions, and velocity conditions, I think it's too much to worry about the difference between 1D and 2D. It's beyond our understanding of everything else that's going on, the growth of vegetation, trees falling, debris accumulation, all these other things overwhelm, what you need to be thinking about instead of small changes in Manning's N. At least for the kind of work that we discussed here, design of stream restorations and and other kind of problems that you're trying to solve around a bridge or somewhere else. But for flood elevations, it's probably a very important thing to think about.
Excellent. Thank you so much. And we are just at 1 o'clock. So I would like to say thank you so much, Jesse. Thank you so much, Art, for presenting, sharing your work with us. This was really great. Thank you, everybody, for attending the webinar and for your wonderful questions. If you're not signed up for our newsletter, again, go ahead and sign up so you can find out when the next webinar is. And we'll see you guys again. Thank you guys so much.
Thank you.
Thank you.